Now, in the previous lecture, all the parts of the previous lecture, the goal was to really talk about how do we, what is the theory behind how the property tables are organized and constructed. In this set of lectures, our goal is going to be, so this is lecture 6 for us. Our goal in lecture 6 is to really focus on talk about how do we actually use these property tables. So that's going to be our goal here. Okay. Now, so it's more practical to publish this information in tabulated data form. That's what we've learned about teaching engineers and teaching people about how to use these property tables. We've learned in the last few years that that's really kind of what we want to do is publish this information in tabulated form. See if I can adjust the wide angle just a little bit there. So we're going to talk about how do we use these tables, right? So we've already gone through a tour of these. This is table A5 in the English units. And again, just draw your attention to A4 has nice round values of temperature, where A5 has nice round values of pressure, and that's true in both the English and the metric tables. Notice this one row right here. Who can tell me, well, think about why is this row, this value of pressure special? Go ahead and pause. Figure out what's special about that pressure value. All right, you got it? This is 1 atmosphere. So you have a row specifically for 1 atmosphere. You'll find a similar row, or essentially the same row in the metric tables of 101.3 kilopascals, 14.696 psi pounds per square inch absolute. That is 1 atmosphere. So you have a row for 1 atmosphere in both unit sets. But you see here you've got specific volume, internal energy. You've got this one enthalpy, this H value we haven't talked about yet. And then you've got entropy. Okay, so let's talk about enthalpy, this H value. What is that? The H value. So if I draw a capital H is the sum of your internal energy, capital U, plus the product of pressure times total volume. And lowercase h, which is what you find in the tables, is equal to lowercase u, the internal energy, specific internal energy per unit mass, times the product of pressure times specific volume. That's volume per unit mass. What is it? It's the simplest way to think about it is, or what we normally use it to describe, is the energy of flowing mass, right? So it's there, at least that's in a normal situation when I would need to sum U and PV together, is when I have flowing mass. And we're going to talk about that in chapter 5, why that's the case. But for us right now, it's just this is the enthalpy. By definition, is the sum of U and PV values. If you went in these tables and if you took then the product of the pressure and the specific volume, and you multiplied those together and added it to the value for the internal energy, you would get the same value you would get for enthalpy, right? And you could do that in any number of for anywhere along this table, you would find that to be a true statement. Now, in the English units, you do have to be aware. I've got PSI times cubic feet per pound mass, which is not BTUs per pound mass. I'm going to have to do some conversions. It's easy enough to get there, but you do have to be aware of that. So in the metric system, it's fewer conversions, but you still have to make sure your units work out. Okay, so that's what enthalpy represents, is the sum of U plus PV. And again, we're going to talk about a few places throughout the semester where those are valuable quantities, where we don't want to have to every single time make this summation in order to find that value. Having it available to us is going to be valuable. Okay. Using property tables. I'm going to write these down with you. This is something you want to have available to you. This is lecture 6. This is going to be page 1 of something. Using property tables. Right. For us right now, it's just going to be using property tables. Later on, it's going to be determining unknown properties. In fact, you could label it right now, but if we're specifically using property tables, um, step 1 is to identify your substance. And I'm writing the same thing that's on the number 1 through 4 here. I'm not writing anything different. Um, So it's okay if you can't quite see it up here on the little screen. I'm writing the same thing there, but I'm writing it along with you. So you're writing it in your notes is really kind of what I'm trying to do. I'm making you write it in your notes because it's really important. Once you've identified your substance, then you're then you can make some determinations about what your next steps look like. So for us right now, our focus is going to be on water and R134. I often say R134. There's an A after that. There's an A and B isomer of R134, which unless you had organic chemistry, that's not going to mean anything to you, and that's okay. Um, but there, for us, it's just going to be R134, and that's all we have to say there. It's a refrigerant. It's a specific oily substance that undergoes pressure temperature changes for us at very convenient values. So that's the substance we're going to deal with in this textbook. Now, if you look into other textbooks, they'll have property tables for other substances like ammonia, propane. Some older texts might have R22 or maybe even R10 and R12, the old-fashioned freons you might hear people talk about. So some newer texts might have R410. That's a newer refrigerant that we often use, or some other organic substances that now we're having to use as refrigerants in the modern era. Um, but your textbook just gives you property tables for two substances, and the mentality there is if we can teach you how to use it for two substances, the saturation tables for any other substance works the exact same way. So if you did have ammonia or propane, you could pull a similar set of property tables from another source and figure out what properties you needed to size or estimate energy use or how large of a compressor you needed, etc. Right. So we just have water in R134. The way we use these tables work the same for other substances as well. Step 2, once we know what our substance is, that tells us we can go to the right tables. Step 2 is identify known properties. All right, so I'm going to add a little bit here. You need at least two. Right? You need at least two properties. That can be P, little v, T, U, H, S. You can even know the phase. If you happen to know the phase, sometimes that serves as a second property, but I need at least two properties. So that becomes very important that we start recording our givens out of the problem statement. We organize the information that's given to us in a format that's very useful to us. Step 3, determine the state. Right? So state is one of those things we said that's in chapter 1. You can read it. It's important. And we normally don't have class time to talk about all the definitions. State is one of those. State means once I know the state, that means I know where I'm at on the PVT surface that we talked about in lecture 5. And once I know that, that means I can describe all of the properties of my substance at that point. So knowing the state is important. There's this bullet here that says watch units, right? So make sure you use the appropriate unit set of tables. Don't just convert everything to metric. That's pretty lazy. I get that there's some advantage as far as units go, but units really aren't that hard once you figure them out. The biggest thing is once you convert to units, you might line up with nice round values in English units. You convert them to metric, you're no longer going to line up with nice round values, and you're going to be between rows in the tables, and it's going to be a lot more work for you than it's worth. Sounds like I'm getting a weather alert on my phone. And then there's this subpoint here of determine the phase. Determine the phase. And then once we know that, once we know what our phase is, which basically is which table, which row or rows are we between? I'm going to write that. That's important enough. I'm going to write that on the slide here in parentheses. Which table and which rows. So row or which rows are you between? Which table, which rows? Once you know the phase, you can dial in, figure out the state. Once you know the state, you're going to know which table, which row. And once I know which table, which row, that means that I can record your desired or needed properties, which is really the whole goal. So I say a couple of things to my students when they're in the classroom with me. Write this down, have it handy. The first 100 times or so, you need to figure out properties for an unknown, unknown properties for a substance. You want to have this handy. Um, After about the first 100 or so times, you'll get kind of used to it and you won't think too much about it. You can kind of go through these steps in your head. So for the next 1,000 or so times over the course of the semester, you'll get very comfortable with it. And sometimes students kind of snicker a little bit when I say, well, for the next 1,000 times, you'll get comfortable with it. And then by the end of the semester, they understand that I'm really not kidding. For about the first 100 or so times you go through this process, you'll want to have this handy. But then after that, for the next several hundred, maybe 1,000 times that we do this, it will become second nature. By the time we get to chapter 5 problems, you'll realize that this lengthy, drawn out process that sounds terrible and is miserable when we're trying to do it in chapter 3 is just a small substep in a larger problem that we have to do this multiple times in one problem to get all the things to go into other big long equations that I'm having to solve. This is a step in the process. So we want to get really good at this. Using property tables is a skill, and with practice, you'll get better. So that's why I say first 100 or so times, have these steps handy so you know what they are. The next 1,000 or so times, you'll get pretty comfortable using. Now, notice this little step, this sub-step under 3 here that says determine the phase. Honestly, that is the hardest of all of this stuff that's going on here. The rest of it's pretty simple, but determining your state, which means you got to determine your phase, therefore you know which table, which row, so I know what my state, all my properties are. That's a big deal. And that normally falls into one of two categories. And what I always suggest to people is just draw a diagram, right? Especially when you're kind of getting used to it. After a while, you can kind of see the diagram in your head. But remember in the last lecture, we talked about your pressure and volume graphs kind of look like this, where you've got this dome region, right? You got this dome region. And you actually end up looking kind of the same way if I put temperature over here on this y-axis. So I can put pressure or temperature, and I could put V down here on the x-axis, and I get the same looking diagram. Um, and the neat thing is, I could put V, I could put U, I could put H, or S down here on this x-axis, and the diagram looks almost the same. There's some variation between the different properties, but for the most part, it looks the same, and mechanically it works the same. Is given temperature, at your given temperature, you're going to want to know, am I between the values for liquid and the values for vapor? And once I know that, then I can figure out where I am in terms of phase. Once I know my phase, then I'll be able to find the rest of the information. Okay. Um, and then also the other possibility is I could be given pressure and temperature. So if I'm given pressure and temperature, remember the PT diagram. And if we're not worried about the solid transition, this is all it looks like. Your pressure versus temperature just looks like this, where everything to the left I apologize, this is bouncing around on me. Everything to the left of that curve is liquid, and everything to the right of that curve is vapor, which we have the same thing over here, right? We've got vapor over here. I've got compressed liquid on the left, and I've got superheated vapor. Superheated vapor. Same thing over here, superheated vapor. That's my 15-minute alarm. So I've got superheated vapor on the right. And it's the same no matter what combination I have. I've got compressed liquid on the left of the curve, superheated vapor on the right of the curve. And what I need to know is at the given, basically at the given pressure, right, at a given pressure, I can go look up what is my saturated or boiling temperature. And that'll tell me, and I just plot it on this, roughly on this curve, and that'll tell me whether I'm in the liquid vapor region or if I'm on the curve, which means I've got some sort of a mixture. Okay, that's a decent enough stopping place. We'll pick up from there on the next video.